lecture, 15 minutes lecturing time for this semester, okay? Now, all right, the role of the integral term, okay? It will drive arrow to zero. Why? Because as long as there is persistent non-zero arrow, the integral or arrow will continuously grow, all right? Because of it calculates the accumulation, okay? If the zero is not completely zero, it will keep accumulating. And this growing output from the controller act as a continuous push on the system, okay? And the response of the controller will therefore become stronger and stronger, okay, to counteract the accumulation of the arrow, okay? And such a action will only stop when the arrow is exactly zero. Okay, please do not talk, okay? Thank you very much for your silence. Okay, it will only stop changing when the arrow is exactly there. So this mechanism of integral control ensures that the system keeps correcting until steady state arrow is eliminated completely, all right? That is why increasing the time number of the Lagrange function is very helpful for us to reduce the steady state arrow, okay? Let me study a simple example, okay? Steady state arrow for first order system, okay? This is a first order system. Apparently, the time constant is t, and what we have here is a proportional control. And from the Lagrange function, apparently in this particular case, the time number is zero, okay? Now, what is the output arrow of this feedback control system based on these equations that we have already seen many times? It is this, okay? And since GC is this, G is this, which is just nothing but a K. All we need to do is plug these terms into this representation, and this is what we will come out. Remember that here, one thing I need to address is that here we are studying the step response of this feedback control system. So the nominal input is 1 over S, okay? So this is the X domain representation of the arrow. Again, by applying final value theorems, we know that the steady state arrow is this. Now, this conclusion is in agreement with what we have learned. That is, by increasing K, we increasing the loop transfer function, and as a result, we can have smaller steady state arrow. All right. Now, this is the result of the computer simulation of this feedback control system. As you can see that the steady as time progresses, the output, the actual output and the desired output, between them there is still some minor difference, which is this 1 over K plus 1. So by using larger proportional gain, okay, I can reduce this steady state arrow. But remember, there is a side effect, all right? I may end up with system with smaller phase margin and gain margin, all right? Now, how do I deal with this problem? Let's just, for the same plan, for the same system to be controlled, all I need to do is to increase the time number from 0 to 1. So let me replace the proportional control with the integral controller by using the same equation. But the only difference here is the GC here is no longer just K, but K over S. But I will come out with this result for the steady state error of this closed-loop feedback system. Again, by using final value theorems, it is easy to see that when x goes to 0, this numerator becomes 0. Therefore, I have 0 steady state error. And we expect this result because this is a type 1 system. And from this table, we know that for a type 1 system, when encounter state, when the nominal input is a state function, we always has a 0 steady state error, which we have just confirmed from our examples. All right. Now, okay. Now let's look at another examples. Here, what we have is not just a proportional controller or integral controller. What we have is a PI controller. Now, the control system, the process to be controlled remains to be a first order system where tau is its time constant. Here, the transfer function of the PI controller is this, K1 plus K2 over S. And the loop transfer function, blah, 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 do something like this. Apparently, with PI control, we have a type 1 system. Since we have a type 1 system, we expect we have 0 steady state error if the input is a step function. All right? Now, here, however, if let's drop the value of K2 to 0, then the controller, the transfer function controller will be nothing but K1. Therefore, when K2 is 0, what we have is not a PI controller, but just a P controller. And this case, the truth from the loop transfer function, we know that we have a type 0 system. All right? Now, for type 0 system, apparently we will have, when facing step response, the steady state error will look something like this, right? And well, the position error constant is defined as this. For this particular case, GC is K, and G of X, when X equal to 1 is, GC is K1. And when X is equal to 0, G is K, the value of G0 is K, all right? So the position error constant is this, and this is the resulting steady state error when we have nothing but a P controller. Now, if I have a PI controller, then of course, the steady state error will be 0. But what I need to look at it here is I increase the challenge of the control. Now, I need to deal with range response, which is, again, a moving target. And from the table that we summarize, here, when we have a type 1 system, and when we have the system, and when the system is facing a range input, this is its steady state error. Well, KV is the, well, KV is the velocity error constant. And this, in this case, KV, considering the controller is this, and the system is this, KV is actually the product of K2 times K. Therefore, how do I reduce the steady state error? For this particular system, I can do it by increase K2. Okay. Now here, increasing K1 doesn't help. All right. But by using stronger integral control, I can effectively reduce the steady state error where the input is a range signal. All right. So these mathematical results are actually really helpful because it helped me identify the source of the problem. And after identifying the source of the problem, then I know what to do to make things right. Here, okay, increasing K1 does not help. However, by using larger integral gain, I can actually reduce the steady state error. Okay, now this is a computer simulation result for this PI controller. Okay, now here what I have is not a range input, because for range input it will just go all the way up. I actually have is a series of range inputs with different slope. Okay, as you can see, the actual output, which is represented by the blue curve here on this figure, is doing very hard to catch up with the actual input, to the nominal input, which is the desired output. All right. No matter how hard it tries, there is always a gap between the actual and the desired output, right? Because this is what we get. All right. Okay. So there is always a steady state error. Okay. Now let's look at another example. Here, the difference is that now I need to deal with the second order system. And now what we need to do is to investigate the impact of the input disturbance on the output arrow. Okay. Now we did not discuss that when it comes to the time number of the loop transfer function. We only discuss the nominal input. Okay, but you know, the basic idea of determining the impact of the impact of input disturbance and its relation with the time number is pretty much the same. Okay, now the output arrow due to the disturbance is this. We saw this before. Now the next thing I need to do is recognizing that G is actually this and GC is actually KP. And by plugging this term into this representation, by going through all this algebra to get the transfer function, and by assuming that the input disturbance is a state input with a magnitude of D. Okay, so its Laplace transform is actually D over S. And then we can come out with the transfer function, an X domain representation of the output. And then by using the same technique which we have already used multiple times. That is by using the final variable series, I can determine the steady state error due to the input. All right, same thing happened here. To reduce the steady state error due to the state input disturbance, I need to increase KP, which means I need to increase the loop gain, which means the result we have here is in agreement with the results we saw in the previous two lectures. Okay, now, however, I can eliminate this steady state error by replacing this controller. For example, here, what I have here is a PI controller. Okay, by using a PI controller, I actually change the dynamics of the system. I actually increase the type of the system. And by going through all the algebra, there is nothing fancy here. Every mathematical step involved in this derivation, I'm sure you have already saw it before, and you can deal with them if you want to. And the final result is that I have a zero steady state error. Okay. For today's lectures, we assume unity feedback. We assume, for example, in the beginning of today's lecture, we saw these slides, right? and I assume unity feedback, which means H equal to U. And I have this representation for the output, and then I have this representation for the output arrow. Okay, all these results are based on the assumption that H is equal to 1. But what happens if H is not equal to 1? All right, well, how do I transform? How do I apply the results, apply the things that we have just learned to problems that does not have a unity feedback? Okay, it is actually not that difficult. Not that difficult. Let's say this is the feedback control system that we need to take care. Okay, but all the results we just learned is based on this configuration, which is a unity feedback configuration. And this is apparently a non-unity feedback configuration. Now, what I need to do here is to transform this configuration to this configuration, okay, with an appropriate loop transfer function. All right. Now, the challenge here is what the G star should be. Now, for these two closed loop feedback systems, for them to be equal to the other, what we need to have is that their transfer function has to be identical. That is, the ratio of Y over R has to be the same. For this system, the transfer function is this. For this unity feedback system, its transfer function is this. So the next thing I need to do is that it is required that these two terms have to be equal. So based on this equality requirement, I can determine what G star should be. So to do that, all I need to do is take the product and take this product and make them the same, okay? Now, remember that G and H are all known. The only unknown here is G star. So let me rearrange everything so that G star can be put, any terms involved G stars appear on the same side of the equality. So the first thing I do is let me move G times G star to the left-hand side of this equality, all right? And this is what I will get. As a result, it is easy to see that G star is actually this. So next time, whenever you see a system which is non-unity feedback, and you need to apply results derived from unity feedback system to such a non-unity feedback system, all you need to do is perform this conversion first, okay? Then you can transform this system to this so-called unity feedback configuration. All right. Now, before we go any further, okay, I need you to, let's say, do me a favor. Okay, this is another evaluation, teaching evaluation, a survey, okay? This is required by the school, okay? Please complete this survey. I will leave the classroom for 5 minutes, okay? Now, in that 5 minutes, I hope you can help me complete this survey. If you don't want to help me, that is perfectly okay, okay? Okay, it's a request, not a demand. You have every freedom of not rejecting my request, okay? But I have been asked by the department. They email me several times about getting students to conduct this survey. So let's just, please do me this favor if you can, okay? If you don't want to do that, perfectly okay. I'll come back in 5 minutes, all right? 拜托完成这个这个问卷调查的教学意见评量，5分钟以后我回来。人生真好硬，我很幸福，我很幸福，真的很幸福。What do I feel for my life? You come from nowhere and then it just disappears? I don't think so. Mm. SOP, standard operation procedure. Okay. Thank you very much for your help. Let's finish the last part of today's lecture, which are considered very, very important, okay? Now, in this course of control, I didn't teach you a standard procedure for controller design, okay? Why didn't I do that? Because whatever your control textbooks you read, there is no such a thing called a standard operating procedure or SOP for controller designs. In the real world, controller design is really a case-by-case problem, okay? You encounter different control challenges, and you have to, based on that particular challenges, develop a control methods. And sometimes, even for the same control problem, you need to develop several control methods for different stage of the control process. And this is what we call multi-stage control require multi-method strategies. This is an article I ran into many, many years ago, and it described the hard disk drive position controls methods. In controlling the head of the mechanical hard disk, the control process actually divided into 3 phases: the seek phase, the settle phase, and finally the track follow phase. In each of these 3 phases, the engineers from the IBM apply or employ different control methods. For example, here they use PID control for the track follow. For the settle mode, it uses PD control. And for this mode, it uses so-called high optimal control. This is the original description from that article. Okay, let me break that. Let me break it down into several slides. Okay, now IBM the hard disk control strategy actually consists of 3 phases. The first phase, the goal of the first phase is to move the head quickly, as fast as possible, to reduce so-called seek time. And then the second phase is reduce the leftover vibration. And the final phase is try to land the head precisely at the center of the chosen track. Okay, where the track is, whatever data you want, and that is a storage location of the hard disk. Okay, now so IBM engineers divide the position into 3 modes. The first mode is the seek mode. In this seek mode, the goal here is objective here is to move the head from its current track to the target track as quickly as possible, because as a user, we want our hard disk to be fast. Okay, we want the computers to wait for us, not we wait for the computers. Okay, but some mechanical constraints need to be satisfied or respected, including actuator force limits, structural resonance, things like that. And the thing is, in this case, you have to come up with a strategy for fast disk movement. Okay, to achieve this, hard disk HDD control is typically based on the jack limited motion profile. Most commonly, X-curve velocity profile. So in the seek mode, we first design a velocity profile, and then based on this velocity profile, we develop a trajectory following control strategy, which I will describe in the final part of our presentation. Now, this is a S-curve. Remember, this is time, and this is velocity, all right? So a wave curve implies that velocity increases from 0 to maximum values, okay? Because we want it to move as far as possible. So let's first determine a top speed. This is the maximum speed that hard disk arm can sustain, can provide. Okay, acceleration is ramped up smoothly, which means acceleration, remember, is the slope of the velocity. You can see the acceleration, which is the slope of the velocity, increase gradually, right? And then it also decrease gradually. So when you see the acceleration profile, is actually look like this, okay? This is time, this is the acceleration, okay? This slope is not too large, okay? It actually looks like this. The acceleration increase smoothly, and then it reaches its upper bound, and then it decreases smoothly, all right? So acceleration ran out smoothly, okay? And this is what we call limited jerk. Recall that jerk is a derivative of the acceleration, okay? Now, and then deceleration, it ran down smoothly back to 0, okay? Now, with 0 acceleration, which means velocities will not change anymore, and that means it will stay at the top speed, top velocity, and then velocity is then held. We keep the maximum velocity, all right? And keep it going for a while. So what we have is this, and we keep it at the maximum, and then when reaching our target, we will reverse the operation of the X curve, okay? Which means that which means the acceleration profile will look something like this, all right? Now the X curve, why do we prefer X curve? Because it had limited curve, jerk. Remember, jerk is the slope of the acceleration, okay? We don't want acceleration to change too fast. I'll explain why later, okay? By doing that, we can reduce excitation and we can minimize residual vibration, because this means I can have a smooth landing, okay? Because the acceleration does not change rapidly. It changes gradually in an incremental, stable fashion, all right? Now, during the process, jerk is important. Why is it important? Because when jerk is smaller, we can suppress vibration. High jerk, remember jerk is the derivative of acceleration, correspond certain changes in the acceleration. And acceleration is proportional to force according to Newton mechanics, right? Acceleration is always proportional to force. When A change rapidly, when you have large jerk, that means A can change rapidly. If A change rapidly, force change rapidly. Then if F change rapidly, then it will have rich high frequency components. So increase the high, therefore high jerk corresponding to certain change in acceleration, and it will therefore increases the high frequency components of the actuating force. This excites the structural resonance. Think of the hard disk drive as a second order system. When you see its so-called magnetic plug of the body diagram, you will see it looks something like this. It has resonant peak, and this is the region we don't want to go into, all right? This is the reason why jerk has to be minimized, okay? All right? So that's the first mode. The second mode is the settle mode. The goal here is to quickly damper the head's. Usually, it is running with a task speed, and now you want to reduce the speed of the system. All right, so that is settle mode. Use PD controller to do that. Okay, and this is often the most difficult mode because you will encounter hysteresis and sometimes end up with limit cycles. Okay, hysteresis here as a nonlinear engine that can generate and sustain a limit cycle. We will talk about these two properties in the third mode. Okay, but here you need to understand that why do we need to use PD controller here? Because originally, right after at the end of the SIG mode, the hard disk head is moving in a very, very high velocity. Now, you want to bring down the velocity, and during the process, you want to avoid overshoot. How do you avoid overshoot? You do it if you go, when we go back to the second order system, overshoot is only related to damping ratio. By using D control, we can increase the damping ratio, or at least adjust the damping ratio to reduce vibration, to reduce overshoot, and hence avoid acceleration. Now, the track follow mode use PID controllers. Okay, so the arm can move even with tiny force, low stiffness, friction. It will also run into hysteresis. This is a problem we often encountered in mechanical positioning, in performing position control for mechanical systems, because mechanical systems involve friction. Okay, when we were in our junior high or senior high school, we were told that friction has two modes. Okay, dynamic friction coefficient, static friction coefficients. Okay, friction can have two values. That is not true in the real world. In the real world, friction is actually a function of velocity. Okay, it actually varies with velocity in this function. Okay, the statement that you only have two kinds of frictions is simply a simplification of the real friction requirement. Now, where does hysteresis come from? Okay, it actually presented something like this. Why do we have such a result when it comes to position control? When studying the relationship between velocity and friction, why do we have this hysteresis phenomenon? Because in performing position controls, the entire process can be described by the following phases. Now, in the beginning, let's say we are already very close to our target, okay? Start near the target. Why we start near the target? The control system is near the target position, but a small persistent error exists, but there is still some error, okay? So it's close, but the positioning accuracy is still not good enough. The corrective force commented by the controller is not yet strong enough to overcome the stiction in the moving parts. But because when a object is sitting there still, the friction force is relatively large. Okay, so in the beginning, the force produced by the controller is simply not large enough. But remember that I can use PID control. And the PID control is based on the accumulation of the error. If my force is not large enough, then the object will not move and the arrow will remain the same. And the arrow, if the arrow remain the same, because I integrate over time, so the accumulating arrow will increase, and therefore the controller will produce larger output to try to overcome this problem. Okay, now the object before that the object remain motionless. Okay, now and then controller will start to build force. The controller, especially with the integrated control, keeps increasing its output command, building out the force required to move the object. Okay, and then break away and overshoot. The force eventually overcomes the stiction. All right. Since the force built up is now greater than the minimum force required for the movement, the object finally stops to move. But the object accelerates suddenly and rapidly past the target position. Why does it rapidly pass the position? Because the friction, once the object moves, becomes smaller. Okay? And then I will easily overshoot the target. This thing happens in real life. When you try to move the object, a big table, for example, initially, it is very difficult to move it. So you increase your force gradually. And finally, you move the table, but overshoot because the foot friction suddenly reduced. Okay? And then it will end up with this, which means you overshoot and then direction reverse. The position arrow switch signs. The object is now past the target. The controller reverses the force command to push the object back, and it's stuck again. The object slows down and stops. Again, the reverse force is initially insufficient to overcome the stiction in the opposite direction. And the cycle repeats. And the cycle repeats. The reason is that this is the nonlinear engine, the nonlinear property of the system because of the friction. So friction is really a pain in the neck when it comes to actually positioning control for mechanical system. And what happened is that the motion will look like a limit cycle, okay? And the limit cycle is a closed trajectory in a dynamic system that represents the periodical behavior in acceleration, okay? It's called limit cycle because nearby the trajectory neither spiral to forward. This is what we call stable limit cycle. This is unstable limit cycle. When you look at the motion of the object, it typically looks like this, okay? So it ends up with a limit cycle due to this so-called hysteresis effect. And the hysteresis effect comes from now the friction, okay? So the friction in this case is really the source of the problem. I'm sorry. What do I want to say? Okay, here. Hysteresis acts as the nonlinear engine that can generate and sustain limit cycle in a feedback control system. All right? So how do you resolve these two problems? The first solution is tribology. That's somehow you come out with some lubricant to minimize the friction. Okay? The second solution is that, damn, I don't want my object to have any contact. So I use magnetic elevation system. So to separate the object, okay, with no contact. It when the object that I want to move is elevated by magnetic force, then there will be no contact. If there is no contact, there will be no friction force, and that can solve my problem. Okay. Now, the final issue that we want to address is related to the first phase of the hard disk drive system. Remember that in the phase of the hard disk drive system, the goal is to move the hard disk head as fast as possible to get that done, what we need to do is to design a velocity profile such as X curve. Now, the problem is, how do you make your control system, its output, to follow this S curve? There are two possibilities. The first possibility is I have an X curve. This is the desired velocity profile for my system. And then I divide this curve into many sub-intervals. Okay, for each of the sub-interval, what I need to do is point to point. Point to point motion control, which means when going here, when going here from here, when going here from here, I just assume this is my starting point, which is 0, and this is my target. All right, so I have a constant desired output, and that is one solution. And this solution is apparently not very good, because when you see robot dance, at least the old robots, I'm not talking about the state of our robot, I'm talking about robots in the old movie. It moves like this. Its motion is not smooth at all. Why? Because its control strategy is based on this so-called point-by-point control process. And we don't want that, because we want the motion of our robot to be silkily smooth. So how do we do that? One way to resolve the problem is what we call computer-talk methods, which is based on inverse dynamics. Okay, let's assume the system to be controlled in this second order system. Okay, X is the displacement and F represent the force. Let's assume the desired trajectory, which can be an X curve, has already been determined and is denoted as SD of t. All right, so what I want is to ask the system produce output to follow this so-called desired trajectory, to perform so-called trajectory tracking. And I define the tracking arrow as the desired X with the difference between desired X and actual X. Now, how do I determine FT? I use feed-forward control methods by using the method of inverse dynamics, because I know what the desired output is. All right, so I can take its derivative, I can take its second derivative, and then I plug XD dot and XD double dot into this equation, and accordingly I computing the resulting corresponding FT. Okay, this is what we call inverse dynamics. When FT is known, XT need to be solved. This is what we call direct dynamics. Mathematically, it involves the solution of an ordinary second-order differential equation. But in inverse dynamics, X is given. All you need to do is to determine its derivative and double derivative, and use simple, straightforward multiplication and addition algebra to determine the corresponding f of t. This is what we call inverse dynamics. So then I already know what the actual force should be as a function of time. Okay, how the force should vary with time, so that the X, the response of the system will follow my trajectory. And that is exactly what we do for robots. we pre-plan the trajectory for every robot, every degree of freedom of robot, and then we use this computer torque techniques to determine the required torque for every motor. Give me a few more minutes. I'll wrap it up as soon as I can. All right. Now, but plug, and then the FT also, in addition to the terms computed from the inverse dynamics, I also need to include feedback. All right. Okay. So by plugging this into this, what I will get is this. All right. By putting things together, this is what I will get. Okay. By dividing everything by m, this is the error equation, which is a standard second order system without any input. And by tuning KD, I can actually determine the damping ratio of this second order system. By changing the value of Kp, I can actually determine the natural frequency of this second order system. And I can therefore effectively control the tracking error. If you want to do robotics, if you want to design robots, this is the way to go. Okay. Now, but of course, it has some limitation. The first and most important limitation is it is sensitive to modern errors. All right. So this parameter is be very, very accurate. All right. Now, all right. Okay. That's all. Okay. Final exam is coming 7 days from now. Any question? Any question? All right. I will only answer question regarding to final exam when everybody's during the class. Okay. Right after class, any individual question regarding the final exams, I will tell you right now that I will not answer. That's the first thing. The second thing is we already have a very clear policy regarding to grading. Okay. So whatever your grade is, it all depends on your performance during the exams. Of course, there are some rules, okay, because I want your grades to be good. All right, okay. So whatever your grade is, it is the number that really talks. Please do not come to see me just because, Professor, please give me one more points, because if you give me one extra points, I can upgrade my grade level from A to A plus. Oh, Professor, please give me one more points, because if you give me one more points, I can graduate in 4 years, not 5 years. Okay, don't do that. Don't bad for grade. We just love it. But if I do anything wrong in the grading, you can come and argue. Okay, I will listen very carefully. But other than that, please don't negotiate for grades. Please. All right, that's it. Okay. Thank you very much for this occasion, for your participation. I wish you the best for the final and the coming winter section.